Hello again. So today we're looking at being able to plot and recognise trigonometric graphs. So that is graphs. So they are graphs involving the sine, cosine and tangent. Before we get too far into this, we need to actually take a step back and we need to recall SOHCAHTOA. So this is basic right angle triangle trigonometry, where we have a right angle triangle, and if we're looking for an angle or have got an angle here, we recognise that opposite that angle is the opposite side. We recognise opposite the right angle is the longest side, and that's known as the hypotenuse, and the one that's next to the angle is known as the adjacent. So that's just showing this bit here. Now we're not going to look at the tan straight away, so we're going to deal with the sine and cosine. So we've got the sine of theta is equal to the opposite over the hypotenuse, and the cos of theta is equal to the adjacent over the hypotenuse. And obviously this is correct for angles less than 90 degrees in a right angle triangle. Okay, let's have a look at taking this a step further. So we've got an x and y coordinates here, and we've got a line, and at the end of that line is point P, and that is at coordinates x and y. So what do I mean by that? Well, if I just drop a line down here that is perpendicular to the base, or perpendicular to the x-axis, you can now see that you've got a right angle triangle. This distance from 0 to this point P is x, and the height from 0 up to point P is y. So we can see this point P is known as x comma y. That's the coordinate, and no matter where that point is around here, we could move this line to different places, but we draw the same triangle. So if I just draw another one quite quickly, so I could do the same here, and again I could drop another right angle. That distance is still x, that height is still y, so that point P is still at xy. Let's get rid of that. So the next thing we need to put on here is the angle. So we haven't yet established that. We've got the right angle triangle. So our angle going anti-clockwise, so our angle going this way anti-clockwise, is known as theta. Right, so one thing I didn't do here is I didn't designate the length of this line. So let's designate the length of this line. The length of that line is 1. The coordinate is xy. Obviously will change depending on theta. So now let's bring these two things together. So we know that the sine of theta, well, the sine of theta remains the same, is equal to the opposite, well, the opposite is y, over the hypotenuse, and the hypotenuse is 1. Well, anything divided by 1 is just itself. So therefore, we can say that the sine of theta is equal to y. So in other words, y is equal to sine theta. Let's look at cosine. So the cos of theta is equal to the adjacent, well, the adjacent is x, divided by the hypotenuse, and the hypotenuse is still 1. And again, anything divided by 1 is itself, so therefore we can say the cos of theta is equal to x. Let's just rearrange that the other way around. So we can say x is now the cos of theta. What does that mean? That means we can actually get rid of the x and y. So now, rather than having x and y, we can say that point P is at cos theta sin theta. Let's bring this together. So in this first diagram, we're going to deal with what's called the first quadrant. Now it is this area here that's known as the first quadrant. So if we have that line measuring 1, and that's point P, which we know is cos theta sin theta. So the angles for the first quadrant lie between 0 degrees and 90 degrees. So let's look at the second quadrant. So this is called the second quadrant. Again, drawing the line, which is again unit 1. Point P, we know, is cos theta sin theta. Now the angle is measured from the x there, so that there is our theta, and we now know that the angles for this quadrant lie between 90 and 180 degrees. Moving on to the third quadrant, so this is the third quadrant. Again, showing our unit line, point P is still at cos theta sin theta, and the angle now, again from the line x all the way around here, so that theta there is between 180 and 270. So we know that the angles for the third quadrant are between 180 and 270. And finally, the fourth quadrant, which is this one here. Again, there's the unit line. There's point P, still at cos theta sin theta. Now the angle goes all the way around there. So that now is theta. And that would lie between 270 and 360 degrees. So let's take this now and find some coordinates. So again, for this question here, we know that is 1. We know that is point P, which is at cos theta sin theta. So let's say theta is 50 degrees. So in this case, we're going to find P. So P is cos theta, which is cos 50, and it is sin 50. So if we put both of those into our calculator, we can see that P, or the coordinates of P, are 0.64 to 2 decimal places and 0.77 again to 2 decimal places. So that point there, you can see it's 0.64, 0.77, that coordinate is. Let's look at one more. So if we just put one down here, again, it's a unit. Let's say this angle here is 230 degrees. So we do exactly the same thing. That is point P, and we know that point P is cos theta, sin theta. So in this case, the coordinates of P are cos 230, and that is minus 0.64, then sin 230, which is minus 0.77. Now you might notice something here. You might notice the same digits, one both positive, other one's both negative, and that is basically because it's 50 degrees from this line here, which is the same as this here. So you're getting the same. So what you need to recognize here is you're getting the same size triangle. So now we can plot something called the sine curve and the cosine curve. So we're going to plot y is equal to sine theta first of all. So what we do is we take the values of theta, which are here, and we place a number of these values in to find the value of y. Notice it only goes as high as 1, and that's because we had a triangle with a hypotenuse of 1. So let's put 0 into this. The sine of 0, if you put it in your calculator, is 0. Next one to put in is 90. So if you put sine of 90, you are going to get 1. Then the sine of 180, you're going to get 0. The sine of 270, you're going to get minus 1. And the sine of 360, you're going to get 0. Now all we need to do now is draw a smooth curve through those points. So that is the sine curve drawn. So what we can say here is the sine curve above 0 has a symmetry around about 90 degrees. If you look at this carefully, if I draw a dashed line there, you can see the symmetry here. And then you can see that actually below 0, it has symmetry at 270 degrees. So why are those symmetries important? So the reason why those symmetries are important is we can actually use them as a mirror line. So for example, if we look at the sine of 60 and also the sine of 120 degrees, we can see, if we look at this here, that actually they're both the same. So the sine of 60 has the same value as the sine of 120. And we can do the same with a sine of a 30 and a sine of 150. And also we can do the same with anything on the mirror line of 270. So again, we can look here, sine of 210 and the sine of 330 are the same. They're roughly minus 0.5. That's why the symmetry about 90 and also 270 is important. So as we saw, sine of 120 gives the same value as a sine 60. And that will also work for things like sine of 165, which is equal to the sine of 15. That is the same as saying sine of theta is equal to the sine of 180 minus theta. Okay, so let's plot the cosine curve. So we're now going to look at y is equal to the cos of theta. So we do exactly the same thing as we did before. We replace theta with 0, then 90, then 180, then 270, then 360, and we plot that graph. And hopefully you can see that's the same curve, just shifted by 90 degrees. And if you look carefully, you should see symmetry around the 0 axis for this part here. You should notice symmetry around the 180 axis for this section, and then symmetry around the 360 degrees for that curve there. And that means we can do the similar things we did with the sine curve. We can recognize values that are the same. So if you looked at the cosine value here, that would give you the same value for the cosine of the negative version of that. So we're going to look at the cosine or the cos of 300, and that is here. It's around about there. We're going to look at what other point in the curve we get the same value. So if we go across, it's clear we get that roughly here. Okay, my drawing's a little bit off. It's meant to be just more on this line here. So that would actually be 60 degrees, and that one there, as we said, it was 300. The cos of 300 has the same value as the cos of 60. And in this case, the relationship is slightly different, where we have cos of theta is equal to the negative cos of 180 minus theta. So there we have it. We have the cosine curve and the sine curve. So we're going to plot y is equal to tan theta. Well, if we use our calculator and put tan 0, we get 0. Tan 30 is around about 0.58. Tan 60 is square root of 3, which is 1.7. And the closer to 90 you go, the closer to infinity. So if I do something like the tan of 89, you're going to get 57. And if you put 0.9 in there and more 0.9s, that increases significantly. Can't put the tan of 90 in there because, as I said, it tends towards infinity. So in other words, what's happening here it's getting closer and closer to this 90 line, but doesn't quite reach it. Now we can do the same for minus 30 and minus 60. So we'll get the same values for that, but in a negative. So we get minus 0.58, you get minus 1.73. And again, it tends toward that line. So if we draw that one in now, it will look something like this, where the graph gets closer and closer to that 90 point, but not quite reaching it. So now if we go to the tan of 120, 150, 180. So now if we do the tan of 120, you're going to get around about minus 1.7. The tan of 150, you get minus 0.58. Tan of 180, you get 0. Tan of 210, you get about 0.58. Tan of 240, you get 1.7. And again, getting closer to 270 and closer to that 90, you're getting toward infinity. So if I draw that one on, so there we go, and you can see it's exactly the same as that. Now what happens here, that actually repeats again here, and it repeats again here. There we go, we've drawn y is equal to tan theta. So you can see it repeats every 180 degrees, 0 to there, 180, and it repeats again at 360, and repeats again at minus 180. So this line repeats every 180 degrees from the 0 point, and we have what are called asymptotes at minus 90, 90, 270, and going on every 180 degrees. So an asymptote is a straight line that a curve approaches but never quite reaches. So in this case, the y value of the curve tends toward infinity but doesn't quite reach that dashed line. So in other words, the graph gets closer and closer to the line but never reaches it. So you can use this graph to find trig values for any angle. And because the graph of y equals tan theta repeats every 180 degrees, the value of tan theta will be the same as the value of tan, and in brackets 270, minus theta. So we can say that tan theta is equal to tan 270 minus theta. So if we look at this, we can ask a question such as, what other places do we get the same value as we do at tan 60? So here is the 60 point. If we go up and we go across, we know that's about 1.7. So we also get the value here, which is this point. And let's just do one more. We get the same value here, which is that point. So we can say that tan 60 has the same value as tan minus 120 and the same value as tan 240. So there we have it. You've now looked at plotting and recognizing the trig graphs. So a quick recap. You have the sine curve in red. The sine curve starting from 0 reaches a point of 1, back to 0 at 180, reaches a point of minus 1 at 270, and back to 360. Then you have the same curve for the cosine, apart from it's shifted back by 90 degrees, so it starts at 1. And then finally, we have the trig curve, which tend towards infinity. They don't actually ever stop, so they don't ever reach the minus 90, the 90, and the 270 points. As always, if this video has been of use, please like and subscribe. And my next video is on the transformation of graphs.